The particle that knows it's being watched. You believe that reality is a fixed, solid thing. But what if I told you the universe waits for you to look before deciding to exist? This isn't philosophy, it's a proven, terrifying fact of physics, and it means the world you see is a story you are helping to write every single second. This is the story of the double-slit experiment, the absolute bedrock of quantum mechanics. The setup is simple, a barrier with two thin slits and a screen behind it. The projectiles are photons, single particles of light, fired one at a time. The common sense belief is that firing tiny bullets through two openings will create two simple lines on the screen. But when physicists performed this experiment, that common sense reality began to fray at the edges. Instead of two neat lines, they found disturbing evidence, a complex pattern of dozens of stripes. It was an interference pattern, the unmistakable signature of waves crossing and combining. For this to happen, each individual photon, traveling alone, must have somehow passed through both slits at the exact same time, behaving as a wave of pure potential. It was a ghost that interfered with itself. Baffled by this impossibility, scientists placed a tiny detector at the slits. This single act of observation shattered the mystery and replaced it with an even greater one. The moment the detector was turned on, the interference pattern vanished. In its place were the two simple lines they expected all along. It was as if the particle knew it was being watched, because the very act of measuring its path forced it to abandon its ghostly existence and choose a single, definite reality. The math confirms it, and a century of experiments have proven it. The universe is a puzzle where the observer is an undeniable part of the equation. But this leads to an uncomfortable question. If a single particle's reality is this fragile, what happens when two particles are born linked, their fates tied together from the very start? The twins linked across space. Albert Einstein called it spooky action at a distance, a phantom connection he refused to believe was real. He ridiculed the idea that two particles, born from the same event, could remain perfectly linked across the entire width of a galaxy. But the universe, it seems, is far spookier than he ever imagined. This phenomenon, quantum entanglement, describes an unbreakable bond that transcends space itself. To understand the disturbing evidence, first imagine a classical version. A machine creates two coins, one guaranteed heads and the other tails, and seals them in separate boxes. You send one to the moon. When you open yours and find heads, you instantly know the other is tails. The outcome was always determined, but the quantum world plays by different rules. Entangled particles have no predetermined state, existing in a ghostly superposition, a shimmering blur of every possible outcome. Using our coin analogy, the particle in your box isn't heads or tails, it's both. The moment you open the box and observe it, forcing it to become heads, its twin, even light years away, instantly snaps out of its own blur and becomes definitively tails. The connection is instantaneous. This was a bridge too far for Einstein. His theory of relativity was built on a universal speed limit. He argued this paradox proved quantum mechanics was incomplete, believing in local realism, the common sense idea that objects have definite properties and can't be influenced by distant events. He believed the particles must have carried secret instructions, hidden variables, that decided their fate from the start. For decades, it was a philosophical war. Was the universe sensible, as Einstein believed, or a realm of phantom connections? The math insisted they were a single system, one destiny stretched impossibly thin across space-time. This raised an uncomfortable question. Could a test be designed to force the universe to show its hand and prove once and for all who was right? The test that proved Einstein wrong. For decades, the strangest ideas in quantum mechanics were ridiculed as mere theory. They were ghosts in the mathematics, debated by giants like Einstein and Bohr, but with no way to prove them. That all changed in 1964, when a physicist named John Bell devised a test that would put reality itself on trial. The world of physics was caught in a stalemate between Einstein's common-sense universe of hidden variables and Bohr's strange and interconnected quantum world. It was a deadlock, until John Bell created not a new machine, but a new question. His creation, Bell's theorem, was a masterpiece of logic in the form of a mathematical inequality, a definitive line in the sand. In essence, it predicted the statistical limits for how correlated two entangled particles could be if Einstein's hidden variables were real. But here was the disturbing evidence the theory proposed. If the spooky connection was real, that limit could be broken. The correlations would be stronger than any version of common sense could possibly allow. The challenge was laid down, but it took nearly 20 years for technology to catch up. In 1982, a team in Paris, led by physicist Alain Aspect, finally did it. They generated pairs of entangled photons, firing them in opposite directions toward detectors whose settings could be switched at the last nanosecond. They were testing a truly instantaneous connection. The experiment was run, the data was collected, and the verdict came back. Again and again, the results shattered Bell's limit. The numbers proved the correlation was far stronger than Einstein's reality would permit, confirming his hidden variables did not exist and that our universe is not locally real. The connection is a fundamental feature of our cosmos. The test had been performed, and the verdict was in. The universe is fundamentally interconnected in a way that defies our most basic intuitions. Which leads to a deeply uncomfortable question. If a connection can exist that transcends space, could it also transcend time? An echo from the future. We live our lives moving forward, secure in the knowledge that the past is fixed and the future is unwritten. We ridicule the idea that the arrow of time could be anything but straight. But what if that security is an illusion? A landmark experiment suggests a choice we make in the present can reach back and rewrite what has already come to pass. This is the delayed choice quantum eraser experiment, and it provides some truly disturbing evidence. In this setup, a special crystal creates a pair of entangled photons. One, the signal photon, is sent to a double-slit screen. The second, the idler, travels a much longer path and acts as a tag, carrying the which path information. Crucially, the signal photon arrives and makes its mark long before the idler reaches its destination. The particle's history, it would seem, is already written. Now, after the signal photon's journey is over, the experimenter makes a choice. They can either measure the idler photon to reveal which slit its twin went through, or they can erase that information, making it forever impossible to know. This choice is made in the future, long after the past event has been recorded. The result is impossible. When scientists analyze the data, they find the pattern on the main screen has changed based on their future choice. For all the photons whose path information they later chose to read, the screen shows two simple lines. But for all the photons whose path information they chose to erase, the ghostly interference pattern reappears. The choice made in the future dictates the physical behavior of the photon in the past. The experiment leaves us with a staggering conclusion. The past is not fixed. It remains a superposition of possibilities, collapsing into history only based on the choices we make later. This raises an uncomfortable question. If knowledge from the future can alter the past, could you use this ghostly connection to detect a threat in the present without ever laying a finger on it? The bomb without a trigger. Imagine a collection of bombs armed with a quantum sensor so sensitive that a single photon will set them off. How do you find the live ones without detonating them? Classical physics ridicules the task as impossible, demanding that to know something, you must interact with it. Knowledge requires contact, but quantum mechanics offers a way to see in the dark. This is the Elitzur-Weidmann bomb problem, and its solution lies in superposition. The setup is an interferometer, a device of mirrors that splits a photon's path in two, then merges them. Normally, the photon travels both paths at once as a wave, interferes with itself, and always arrives at detector A. It is never seen at detector B. Now, we place a bomb on one of the two paths. Here is the disturbing evidence, presented in three possible outcomes. 1. The bomb is a dud. Nothing changes, the photon hits detector A. We know it's safe. 2. The bomb is live. There's a 50% chance the photon takes its path and the bomb explodes. We fail. But there is a third outcome, a quantum miracle. There is a 25% chance the photon travels the safe path. The mere presence of the live bomb on the other path acts as an observation, forcing the photon's wave to collapse. It becomes a particle. And because it can no longer interfere with itself, it suddenly has a chance of arriving at detector B. That is the impossible solution. If a photon ever clicks at detector B, we know with absolute certainty there is a live bomb on the other path. We performed an interaction-free measurement, seeing the bomb's shadow without ever shining a light. This raises an uncomfortable question. If a particle can know something is there without touching it, what other laws can it break? Could it use this same ghostly logic to be somewhere it has no right to be? Like the other side of a solid wall? The particle that cheats reality. The world we see is governed by simple, unbreakable rules. We ridicule the idea of walking through walls. A ball cannot roll up a hill without enough energy to reach the top. This is the world of classical physics, where you must pay the toll to overcome an obstacle. But at the quantum level, these rules are ignored. This phenomenon, known as quantum tunneling, is a form of cosmic cheating that makes life in the universe possible. The disturbing evidence begins with a particle's nature. An electron's existence is a wave of probability. When this wave hits a barrier, most of it reflects. But a tiny, ethereal piece of the wave doesn't stop. It leaks through, creating a faint echo of possibility on the other side. This means there is a small, but very real, chance the particle will simply cease to exist on one side of the wall and instantaneously reappear on the other. It tunnels through a space it has no right to be in. This isn't a theoretical curiosity, it is a cornerstone of our existence. At the core of our Sun, temperatures are immense, yet not high enough for hydrogen nuclei to overcome their mutual repulsion and fuse. By classical rules, the Sun should not be able to burn, but it does because those particles are constantly tunneling through the barrier that separates them. Every photon of light that warms our planet is a result of this quantum sleight of hand. This ghostly action is not confined to the stars. The microchips in our computers and smartphones function because electrons tunnel through insulating barriers, completing circuits in impossible ways. Our entire digital civilization is built on this act of cheating. This raises an uncomfortable question. If a single particle can exist in this strange state of here and over there, what happens when we tie that uncertainty to something much larger, forcing a creature to be both dead and alive? The zombie in the box. Imagine a sealed box. Inside, a cat is trapped with a device that could end its life at any random moment. The laws of quantum mechanics say that until we open that box, the cat is not dead or alive. It is a ghostly mixture of both. This is Schrödinger's cat. It was conceived by the physicist Erwin Schrödinger, not as a proposal, but as a challenge meant to ridicule the very theory he helped build. He found the implications of quantum mechanics deeply disturbing. A particle could be in multiple states at once, but what happened when that microscopic uncertainty was chained to the fate of a macroscopic creature? The diabolical device he imagined provides the disturbing evidence. Inside the box, a single radioactive atom has a 50-50 chance of decaying in 1 hour. If it decays, it triggers a Geiger counter, which swings a hammer, shattering a vial of poison. The cat's life is now linked to the quantum state of that atom. The cold, strange logic takes over. The unobserved atom is in a superposition. It has both decayed and not decayed. This uncertainty infects everything. The Geiger counter is both triggered and not. The hammer is both fallen and not. Therefore, the cat itself is forced into an impossible state of superposition. According to the unwavering mathematics, it is simultaneously dead and alive. The paradox evaporates the instant an observer opens the box. We find either a perfectly healthy cat or a tragically deceased one. This forces upon us the deepest, most uncomfortable question in physics: the measurement problem. What is it about the act of observation that forces the universe to choose? Does it require a conscious mind? The boundary between the quantum realm of potential and our solid world of actuality remains a profound mystery. But what if observation could be used not just to collapse reality, but to control it? What if, by simply watching, we could freeze time itself? The watched pot that never boils. There is an old saying that a watched pot never boils. We treat it as a metaphor for impatience, a trick of perception we can ridicule. But what if it wasn't a metaphor at all? In the quantum realm, this piece of folk wisdom becomes a literal, physical law, where the act of looking can truly freeze time. This bizarre phenomenon is known as the quantum Zeno effect. It's named after the ancient Greek philosopher Zeno, whose paradoxes argued that an arrow in flight is at rest at any given instant, and therefore can never truly move. For 2 millennia, this was a philosophical riddle, until quantum mechanics transformed it into a startling experimental fact. The disturbing evidence is found by imagining an unstable atom set to decay. Its internal clock is ticking. Now, imagine we decide to watch it. We perform a measurement and confirm it has not yet decayed. We wait a fraction of a second and measure again. It's still there. Here is the quantum twist. Every single measurement forces the atom's wave function to collapse back to its initial, undecayed state. Each time we look, we are resetting its evolutionary clock back to zero. If we can make our observations rapidly enough, faster than the atom's natural decay process, it can never complete its transformation. It becomes trapped in a loop, a state of stasis created by our relentless gaze. This is not a theory. It has been confirmed in laboratories. Physicists took collections of atoms programmed to flip from one energy state to another. By hitting them with frequent pulses of laser light, a form of measurement, they were able to forcibly hold the atoms in their initial state. The watchpot, in this case a cloud of atoms, truly did not boil. Observation is not a gentle glance. It is a physical intervention that can alter the course of reality. This raises an uncomfortable question. What if we could scale this power up, not just to a single atom, but to the entire cosmos? What if a choice we make today could reach across billions of years to change the ancient history of light from a distant star? The choice billions of years old. We believe the past is fixed, a history written in stone. We would ridicule any claim that we could change it. But what if a decision made in a laboratory today could reach back through the eons and define the journey of a single photon that began its voyage before the Earth was even formed? This is the ultimate expression of quantum weirdness, a thought experiment designed by the legendary physicist John Wheeler. The setup is breathtaking. Imagine, billions of light years away, a quasar emits a single photon. On its path to us lies a massive galaxy, whose gravity acts as a cosmic lens, splitting the photon's journey into 2 distinct paths. Both paths, however, point toward a telescope on Earth. Now, fast forward billions of years. It is today. That ancient photon is just about to arrive. And here, in the present, a physicist has a choice. Here is the disturbing evidence. Choice 1. They can configure their telescope to see which path the photon took. This act of observation will force the photon to have behaved as a particle, having taken one single route through the cosmos. Choice 2. They can place a beam splitter at the focus, merging the light from both paths to check for interference. This will prove the photon behaved as a wave, having traveled along both paths simultaneously. The choice we make now retroactively creates the photon's history. Did it travel a single path or both? According to Wheeler, the universe does not assign a history to the photon until we, billions of years later, decide what question to ask it. Wheeler's cosmic experiment suggests that we are not just observers of a pre-existing history, but active participants in its creation. This points to one final, deeply uncomfortable question. If even the ancient past is just an unwritten story, what does that say about the nature of reality itself? It points to one final, terrifying truth, the one that even Albert Einstein refused to believe. Reality as a roll of the dice. For centuries, science has been a quest for certainty, a search for the clockwork gears of the cosmos. We believe in cause and effect, in a universe governed by unbreakable laws. But every experiment we have explored, from the particle that knows it's being watched to the choice that rewrites the past, leads to the same unsettling conclusion. At its deepest level, reality is not a machine. It is a casino. This is the final shattering truth revealed by the mathematics of quantum mechanics. Think back to the double-slit experiment. A single particle existed as a ghostly wave of pure probability, its final destination on the screen a matter of chance. Consider the entangled twins. Their connection was not a pre-written script, but a shared roll of the dice, where the random outcome for one instantly defined the outcome for the other. The particle that tunneled through a solid wall simply won a cosmic lottery, a fluke of probability that allowed it to appear where it had no right to be. Again and again, we arrive at the same core concept. Before an observation is made, the universe is a haze of overlapping possibilities. A particle has taken all possible paths at once. The act of measurement, the simple intrusion of our world upon this quantum dream, forces the wave of potential to collapse into a single, concrete reality. And the specific outcome of that collapse is, by its very nature, fundamentally random. There is no hidden cause, no deeper reason. It is a pure, irreducible chance. This was the one conclusion that Albert Einstein, the man who redefined space and time, could never bring himself to accept. He believed in a deterministic universe, one of beauty and order. God, he famously wrote, does not play dice with the universe. This was not a casual remark. It was a statement of his deepest scientific and philosophical conviction. So, Albert Einstein was wrong. The universe does play dice. But the experiments that broke reality didn't reveal chaos. They revealed a connection. They prove that you are not just an observer. You are a participant. The next time you look at the world, remember, it's looking back. And the game it's playing is one where you are an essential piece.